Good morning. Am I audible?
Yes, sir, you are audible.
Okay. Let us wait for a couple of minutes. Good morning again. Let's get started. Let others slowly join. Now, we have discussed a whole lot on the lambda side, starting from the syntax of lambda expressions, their semantics, reduction, and the typed lambda calculus as to where expressions have types and what are their type checking rules. And we have taken a quite a specific look into lambdas as brought into common programming languages like C++, and also we have looked at various functional programming languages. Now, we would take this forward in terms of looking more into, I mean, little bit more details of the type systems that are normally built for different common programming languages. We'll see what are the features of the type system and kind of how some of these, type checking rules and inferencing can be made use of in the type system to make the compilers more or the runtime systems more efficient. So we'll take a look in module 6. We'll take a look on the type systems of programming languages in generality. The module has been uploaded already by Showman in the Moodle, so you can download and keep it handy in case you need to refer to specific slides. So let me go over to the presentation. So I hope the presentation is visible now. Right?
Yes, sir.
Okay. Okay. So as I said, we are talking about type system. So there's a long list of items the that will do, but it's quite straightforward in that way. But so starting with what is a type system? This is a little bit of a more formal notion that a type system is a tractable syntactic method. This word tractable has to be noted with care because type systems often will come across problems to solve which are not tractable problems, which means that so naturally a type system is working as a part of the compiler, and it has to be very very efficient, if not linear, but it has to be very efficient in that way. So if it has to engage into some intractable problem solving, then it will not be effective. So it is a tractable syntactic method for proving the absence of certain program behaviors by classifying the phrases according to the kinds of values they compute. Since this is, you can say that the type system has kind of a little bit of a negative connotation, that it is not proving, that this thing exists or this will happen or anything. It just says that, well, certain behaviors will not be there, certain undesirable behavior will not be there, and it does that by classifying the phrases. So a program is composed of phrases from the programming language, checking out what kind of values they compute. So we'll see more of that as we go along. But this is the abstract or kind of the more formal definition of a type system. So before getting deeper, let's just take a quick further look into what is a type. That type is a collection of computational entities that share some common property. So so far we had looked at type more from the mathematical perspective. So we said a type is a collection of values uh, which are known a priori, which we say is a domain, and a set of operations which can operate on that type. So this was a mathematical view of that. So when we say int, we have a range, and we know exactly it's a large set, but it's a finite set of values that int represent. And then there is a fixed set of operations that you can do, whether you add, you multiply, you check for equality, and so on and so forth. Whereas if I say a type is a pointer, then again I know a finite set of values for the pointer that it can take, the addresses in the machine, and there is a set of operations like I can dereference a pointer, I can assign a pointer to another, I can check for equality, I can add an integer to a pointer, I can subtract two pointers, but I cannot, of course, add two pointers, right? So uh, would you please mute yourself kindly? Kindly. Please mute. Please mute. Okay. So this is the mathematical view that we took. And so all these operations can be taken to be the common property. But often in terms of dealing with type now, we will go beyond those common properties and we could talk about other properties. For example, one property that is very, very critical in terms of dealing with typed data and their conversions, casting, and all that is how are they represented? Because finally, beyond the mathematical concept, when we are talking about computation here, we are talking about a kind of a von Neumann model, right? So we have a memory which is kind of say byte organized, and everything is represented in terms of bits. So it is also necessary that if we if we say that something is an int, then there is a specific way to represent it so that at any point of time it can be interpreted for the value it is intended to represent. So that has a certain algorithm of laying the bit pattern. It has a certain size which normally will not vary, and so on and so forth. So the property is not limited to just kind of the operations that mathematically we talked of, but it will go beyond that, and it could be several different things that a type, the commonality will talk of. But certainly it is a collection of computational entities, and that commonality of property is important. So we say int is a type, bool is a type, int to bool, this function mapping is a type, and so on. But things like 3, if I say 3, a constant 3 or a constant true, they are not types. Even I'll say that even integers is not a type. You'll argue why even integers are not a type. They have a commonality. The commonality is that every element there is divisible by 2, and certainly it's a finite set and so on. The question is whether the language actually has provided a specific type for that. So there is a distinction between the set of values that are types and the set that are not types, and that is language dependent. So I may design a language where even integers is a type, but if it is not, then if the language has not defined that, then I cannot treat that as a type, because language or the compiler will not enforce that. So that's what the type we are talking about. Now, there are several advantages, uses of type. The three main ones are, naturally, it provides a common name and organization of the concept. By knowing that something is int, we get to know a lot about that concept, which does not need to be elucidated at every point. We make sure that the bit sequence in the computer memory are interpreted consistently. Otherwise, if we just say that I have a bit pattern 1001, this 1001, what it means, what it represents, is not known unless you know that type. It is a type which tells whether it is a representation of a character or a number or something different, right? So interpretation of the bit sequences in the computer memory, and this is what I was talking of, that type here in type systems go beyond the mathematical concept of type. We are talking about the engineering aspects actually. And then it provides information to the compiler about the data that is being manipulated by the program, right? So the compiler gets to know a lot from this information on type, and based on that, it can provide us with a lot of services. So this is what we are trying to basically look at. There are several advantages. Naturally, it helps in program organization and documentation. Separate types represent separate concepts. From the problem domain, we will say, if we are talking about number of people, then we will certainly say that it is a type which is an integer. We actually can go forward and say that it is a type which is unsigned, unsigned integer, because I cannot have negative number of people. So it tells about that concept. Whereas if I'm talking about say the weight of a person, then I would not say that it's an integer. I'll say this is a more like a floating point number, because it can have fractional parts. And it documents the intended use of the declared identifiers. Because when I say int number, it says that the number will be used in this context of having whole number values. If I say unsigned int number, then the number will not take any value which is less than 0, and so on and so forth. So it's a documented use. Certainly it goes a long way, and this part we have seen, you have known for long, you have seen directly that it helps in identifying and preventing errors. It could be compile time, it could be runtime. For example, computations like 3 plus true minus string bill. This in C or C++ or Java would be an error. It's a compile time error, right? And it supports the optimization, because since types relate to the bit organization, so when I want the same kind of semantics of whole numbers, I could use int or I could use short int. If I use short int, knowing that I will never require a number larger than a certain limit, then I'm being able to optimize fewer number of bits, and compiler helps me in doing that. It supports optimization in terms of accessing components of structure by the known offset and so on. So there are several advantages of type in terms of engineering the compiler that goes on. So in this context, what is a type error? We said that we had a type error. So every compiler error is not necessarily a type error, but a type error is the most common. A type error occurs when a computational entity, such as a function or a data value, is used in a manner that is inconsistent with the concept it represents. So every type is representing some concept. Every type has an associated set of properties. Now, computationally, every entity of a type will have to be used in the context in terms of the concept it represents. Right? So the compiler or interpreter can say that what it is. So something like we often can have bad bit sequences. Like floating point representation, as you know, has a separate IEEE standard from integer. So it has a different specific form. So an integer cannot be treated as a valid float, and vice versa. So those are the kind of bit sequence error. If I have declared x as int and try to do this x function call, then it is a hardware error because you are actually looking for an address in the callable space of the machine. Or I'm trying to do a float add of 3 and 4.5. I actually have a hardware error if I directly try to do this, because 3 has a representation in integer which is not the bit representation of a valid floating point number. It could also be in terms of inconsistency with the way the programmer actually wanted to use it. It has been declared as a character and used as an integer, right? Maybe your bit sequence will still support that because it's a simple binary representation, but it's not the intent that the programmer had. So these are different kinds of type errors that can happen. Now, obviously, this is since we are looking at the whole range of programming languages, we must also note that type errors are significantly dependent on the language. What is an error, and what type of error it is depends on the language. For example, if you think in terms of C, C++, then array bounds, that is, suppose I have defined an array of 10 elements and I try to access something which is beyond that, so 11th element, 15th element. In C, C++, there is no, certainly this cannot be statically checked. It's not that it's not there, it cannot be done. You can easily show that. If we do that, then in C, C++, it's a runtime error. But in terms of Haskell or Java, it is a dynamic type error. So it because they have a more strong dynamic type checking, and this a bounds violation turns out to be a dynamic type error. Similarly, trying to dereference a null pointer is a runtime error. Usually, you'll have a segmentation fault or something. In Haskell or ML, they are hidden inside data types. So a null pointer dereferencing is actually an incorrect use of the data type, right? So it is a kind of a static type error for these languages. So the same same physical incidence or same kind of a problem can be treated as different type of errors in different languages. In fact, some languages could treat something as an error, some other language may not treat that as an error. So based on this, there is a notion of type safety. We say how safe a programming language is in terms of its type enforcement. So a programming language is considered type safe if it is not possible to write a program which violates the type distinctions, right? So if you cannot do that, then it is safe. If you can do that, it is not safe. So we can have a kind of, this is kind of an ad hoc, I should say, grouping, not very formal. We are not going into that very formal stuff. So a whole range of languages are considered unsafe, like it's called BCPL, Basic Combined Programming Languages family, which includes C, C++, and several others. So here the type is statically checked. That is the most significant use of the type system, the statically checked at compile time. And it is not safe because of several reasons. For example, the biggest being the typecast. For example, in in C++, you can use a void start type, pointer type, which says that, well, it is an address and could point to anything. You can cast that a pointer into an integer. You can cast an integer into a pointer, and so many things. You can have unions, having a collection of different types, and one of them would only be present. We have talked at length about this. So these are all kind of an excellent recipe to make a programming language unsafe in terms of type, because those cannot be checked easily at all. It cannot be checked almost. Then you have a class of languages which are kind of said to be almost safe. I mean, they're obviously safer than BCPL, like Algol family of languages, Pascal, Ada. Of course, they are not as popular as BCPL family or CC++, but they are much safer than them. They also have kind of their Achilles' heel in terms of pointer use, like dangling pointers could be there. Explicit deallocation could have problems. So actually, if you have dynamic memory allocation and explicit deallocation, particularly explicit deallocation, then it is very difficult to make the language fully type safe, because the programmers can always make a mistake. On the other hand, there are languages which are kind of can be called safe, like ML, Haskell, Java, so which still statically checks, but they do a complete type checking. And in this context, from the type system, you will understand why the garbage collected in Java is important in terms of the type safety, because uh, Java naturally allows you to very freely use dynamically allocated memory. But what it does not allow the user to do is to deallocate an allocated memory. So that's where at the runtime the problems can happen. So it gives that responsibility to a garbage collector, which helps in two ways. One, it kind of relieves the programmer from the burden of managing the dynamic memory, which is a huge issue in C, C++. But at the same time, it relieves the programmer from possible type errors that could be done through this deallocation. I mean, there are programming solutions in C++ which also uh, help you do this kind of type safe deallocation. But that's a programming style. But per se, the language can allow programs which are unsafe, whereas in Java they will not, because this kind of deallocation is not happening. It does not allow pointer arithmetic, so you cannot get into uh, you know pointing to arbitrary locations not representing a bit pattern of a specific type, and so on. And then in the safe group, you have a whole lot of dynamically checked languages like Lisp, Smalltalk, JavaScript, Scheme, Perl, Python, and so on. Right. So there are different grades and different style, and you can see that type safety has to do with what you can check statically and what you check dynamically and what kind of features you support. And there is a trade-off between whether you statically check or you dynamically check. There's a trade-off between whether you allow certain features like pointer arithmetic or you don't. Both exist in the programming language domain, because there are different kinds of requirements. For example, a language like Java or Python can get away without allowing pointer arithmetic or pointer-based low-level access. But C or C++ cannot, because it's also meant to be the systems programming language where you need to really do very low level of, programming, system element access. So it is not possible to write the Java virtual machine in Java. You need C++ for doing that, or a Python virtual machine in Java or Python. You need C++ for doing that. So you need these kind of features as well. You need the utmost efficiency that languages like C++ provide. So you cannot depend significantly on dynamic checking. You have to rely on the static checking, which means that you have partial information about the type system. Whereas in languages like Python, where you are trying to make programming easy for application programmers, commoners, but you do not need that kind of you know very high level of efficiency. It's okay to have a 10 times 20 times slower program execution, but it is very important to have safe programs written by very common developers. So this, requirements vary, and along with that, the type safety and the type systems vary. So if we can say, what are the type systems good for? They're good for obviously detecting errors. They're good for enforcing disciplines in programming through abstraction. They are an automatic documentation of the program. By knowing the type, whether it's built-in or user-defined, you get to know a lot about what is being done. It makes the language safe, so it makes it more and more portable. Naturally, it offers efficiency, because knowing the type, there are a lot of optimizations that the compiler could do, and a lot of dynamic checks that the compiler could actually remove. And there are, of course, there are several other applications of the type systems. If you look at whether it's in network security, or whole lot of program analysis tools that you use to develop software easily, whether you're looking into automated theorem proving in databases, in computational linguistics. There are type systems everywhere. Wherever you have a computing going on, you need to deal with you need to finally deal with bit patterns, but actually let them represent concepts and uh, do the operations in a type safe manner. So type systems are very, very useful in those respects. A quick look in terms of the trade-off between compile time and runtime checking. If we if I go back to slides, on slide 9, you have seen that statically checked and dynamically checked. So statically checked is what is compile time. Dynamically checked is what happens at the runtime. So back to slide 11. So for example, JavaScript and Lisp use runtime checking. So say this is something we are writing here. Say var f sign 3, and we say f2. Now, if we say this, that we are saying that f is a variable which is being assigned the constant 3. So f kind of dynamically you infer that f has a type int. And how we do that, we'll get to that. How the formal system gets into doing that, we'll get to that. But you can very clearly see that here. And what you're trying to do, say by f2, you're saying that it is a function to be called on an integer. So type in is 3. So that's what f was. And the type error that you get is f is not a function. So this is what can be checked at the runtime, and an error could be thrown off. For example, say let's look at JavaScript. I'm writing something which is, could be meaningful, could not be, could be nonsense, whatever you say. Function f(x), f of x, returns, if x is less than 10, then it returns x, otherwise it calls x. Right? So what is x? Naturally, if I'm applying f on x without having higher order functions, then x is some number like integer. Now the point is here, if I happen to use fx with a value which is less than 10, then this is okay. then there's no error. But if it is not less than 10, then it will produce an error. So this is something which kind of runtime checking will bring on to you. As for example, Haskell and Java use compile time checking. So if I have a function called fx, then I must know the type of f, which is a to b, let's say, and x on which f is being called or applied has to be of type a as a data type. So this is what the compiler will. So both kinds of type checking prevent error, whether you do it at compile time or at runtime. Now, naturally, runtime checking slows down the execution because besides executing the logic that you need to, you are also actually doing that checking. Compile time checking restricts program flexibility. Like we showed, this kind of program will still pass through a runtime checker, but not through a compile time checker. For example, in JavaScript, an array elements could be of different types. In Haskell, all elements must be of the same type. So uh, there is a trade-off always between runtime and compile time checking on slide 12. So we can say that a basic property of compile time checking is that it must be conservative. Like it can only work with what is sure will not cause a problem, but not otherwise. So the compile time checking will find all statements and expressions that produce runtime error. Right. So this is the guarantee that you want to give. That well, if there can be a runtime error, compile time will find it. But it may also flag certain expressions as errors, which actually never produces a runtime error. Right. So it does not do the other side. Because often computationally it is not possible to decide that as well. For example, more specifically, if we say that these checkers are both sound and conservative. The first part is a soundness. A type checker is sound if no program with errors is considered correct. If you have a program with error, it will not pass through the compiler. So it's a sound checker. But a type checker is conservative if some programs without errors are still considered to have errors. So it is playing in a conservative manner. Right. So just see an example. So you have a if statement. If there's a complicated expression that could run forever, you do not know. So then you have an expression here, then else you have an expression here, and so on. Right. So it is not possible to deduce whether this expression would produce a true or a false. So static type checking will always be conservative. Like I have a if complicated Boolean expression, then F5, then F15. So where F is this. Now it may so happen that in the space of values that I can have for the Boolean expression, it will never actually produce a false result. If it does not, then I will never call F15. And if I do not call F15, I will only call F5, then this is a perfectly valid program. Right? So, but static typing will have to be conservative. Static typing does not know what this complicated Boolean expression would evaluate to, right? And it does not know because of the earlier point that in a Turing complete language, deducing this in general is an undecidable problem because it certainly reduces to the same, a variant of the halting problem, right? So you cannot deduce that part. So it is always conservative, and it will say that this is not a program which can compile, and therefore it's not considered a correct program. But in reality, it may actually run in every case because that could be what we have. So this is the basic sense of conservativity of compile time checking and the trade-off with the runtime checkers. On to slide 13. So if it's a runtime checker, the advantage prevents type errors. It need not be conservative. Lot more things can be allowed, like in JavaScript. Disadvantage, of course, it slows down the program. If it's compile time, then it prevents type errors again, eliminates runtime tests because you are doing it at compile time, find type errors before execution and runtime tests. So it is got strong advantages, but its weaknesses, disadvantages, it may restrict programs because of its conservative nature, as we have just seen. So in reality, what we find in terms of the type checkers in type systems of common programming languages, it uses a kind of a mix. So most programming language actually use a combination of compile time and a runtime checking. In Java, static type checking is used to distinguish arrays from integers. So that part is done by the static system. The dynamic type checker will check if array bounds are being honored. So it becomes a dynamic error. Similar kind of things exist in C++. You have an RTTI, runtime type information system, which tells you about a lot of things in terms of the objects created and so on. Okay. So that was about the safety and checking. The other concept that we have been talking about, and we will talk more about that, is type inferencing. Type inferencing is a process of determining the types of expression based on the known types of symbols that appear in them. So you are trying to infer. The checker is which goes through the program to check that the types declared by the programmer agree with the language. So checker is given on output, is trying to apply checking rules and finding out if things are consistent, like we have seen checking rules. But a type inferencing engine is given with certain parts where you know the types and certain parts where you may not know the type, and you are trying to infer what type it could have, and then what are the consequences of that inferences. Next slide. So it is, I mean, if you say in terms of checking versus inferencing, standard type checking, int f, int x, return x plus 1. So what will the type checker do? Type checker will get to know that parameter x is of type int. It will get to infer from this that x plus 1 is of type int, and it will check that the return type matches the return type, which is int, right? So, and we have seen this is type checking for function abstraction, and we have seen how to do that. What are the rules for doing that? In the next part, there is a function g which takes parameter y. You apply f on y plus 1 multiplied by 2. So you can do a whole lot of type checking for the applications, which you have also seen. And you get that this must have a type int and it matches the return type. So type checking is given these facts, it is trying to see that I am actually consistent with the types that are given in the program code. So that's the role of the type checker. But if I write something like this here, then what I'm saying is T is a type that I do not right now know. It's called a type variable. Any of you who have done a little bit of programming with templates in a language, you will know that this kind of thing. So where you're saying that f is an incrementer function, whatever that incrementation means. So T is a type variable which is not known at this point of time, but I could instantiate f given a particular type T. For example, I could instantiate it for int, I could instantiate it for float, I could instantiate it for, say, string if the plus operator is overloaded appropriately in the string type. and so on. But when the compiler examines the code, it examines it without the type information. So it can only infer the most general types that could have been declared. Rather, what it can infer is the required set of type traits that would make this valid. For example, a trait required for this type T for the first function to be valid is that it has a overloaded plus operator that takes int as a second parameter. That is a basic trait that you need. The second trait that you need here very clearly, that I mean that's what you can infer without even knowing T. The second trait you need about T is T must have a copy constructor, because you are doing a return here by value, right? So this is T must need a copy constructor. You could of course argue that, or the trait that you need is T is a reference type, so that this comes in as a reference and it is actually being returned as a reference. And in that case, he will say, okay, if T has a trait that it is a reference type, then you are doing something very, very illegal in this program, because you are returning a local object, which is not to be done. So these are the kind of things. But unlike the earlier example where the compiler could specifically check and announce that f has a correct type checked, here it cannot do that. It has to work with a more general types. In terms of G, the traits required will be even more even more involved, because now you need a overloaded plus operator with second parameter int, you need a overloaded multiplication operator with the second parameter in, and so on and so forth, right? So this is the basic difference between type checking and type inferencing. If I may remind you, when we talked about lambda in the earlier module, we have often shown that a lambda may not have a return type. So if a lambda does not have a return type, then what the compiler is doing is it actually doing a type inferencing from the single return statement that it has. So based on the type of the element, the type of the expression that is being returned, the return type is inferred. Whereas if the return type is given, then it is behaving like a type checker, which checks the consistency of the return type specified and the type of the expression that is being returned. So this is, and we will see a lot more of the type checking that we need, the type inferencing that we need. So it kind of, type inferencing is often the mechanism to provide polymorphism, the use of the same expression in multiple types, and it uses type variables. In some cases, the type inferencing algorithm will be able to resolve all type variables and determine that they must be equal to some specific type, either built-in, predefined, or user-defined. In other cases, it may remain unresolved in terms of type variables and may need the specific instantiation for doing the final type checking, what most of this template programming does. So let me stop here once before I start taking examples. So naturally, this has been a overall abstract discussion, and I always love to get to examples. But before that, let me ask if there are questions. Is there any question in terms of, so we have just introduced the basic notions and the terminology. So type system, type errors, type checking, type inferencing, type safety are the basic notions that we have tried to put them on the platter. With respect to several programming languages, this will have to be treated on. No questions, so let me get back and take a couple of examples. Back to the slide, we are we will try to illustrate type inferencing mechanism. So we have talked about type checking in lambdas. So this will be taking steps which are very similar, but kind of closer to what the type systems actually do in programming languages. So we are saying that there's a function fx which is defined as 2 plus x. Right. So we want to infer this, that f is of type int to int, right, based on the right hand side. So how do we go? We know plus is a predefined constant which has a type int to int to int. It takes two integer, gives you one integer. 2 is another predefined type which is int. So that matches here in the argument. So if I apply plus to x, we need x to be an integer, right? Only then we can apply that here. So we need x to be an integer, and if we have that, then we have that fx is a curried version of plus which has a type from int to int. So we infer that given this, two things: one is x is of type integer, and fx f is of type integer to integer, right? So this is a basic, maybe little pathological, little too simple, but this is the basic approach that the type inferencing systems will do. We'll show a more formal way of doing this. This is, as I wrote, this is type inferencing by hand waving, just applying our intelligence. We'll see a more, formal mathematical steps to do this. Another example, let's say f of gh is defined as hg applied to the result of applying h to 0, right? So this is kind of an apply function. F is kind of an apply function. So I said this is the type of f. How? Okay. Let's again try to do the similar analysis. Let's look on the right hand side expression, the body. So h is applied to an integer argument. So we know that the h is from int to something. Now what is that thing? We do not know. What is that type? We do not know. So we represent that by introducing a type variable. So a is a type variable. It could be int, it could be double, it could be string, it could be complex, whatever. Because from this we cannot know that. So it is a type variable, and I can therefore say that h is actually from int to a. That kind of a function. Then g must be a function that takes whatever h returns. We can see here. So the domain of g must be of type a. And then in return something else. We do not know what. It is not constrained to return the same type of value as h. It could be something other than that. So we represent the second possible type as a new type variable b. So g is a to b. So if I put the types of g and h together, we see that the first argument has a type a to b. The second argument has a type int to a. So a function takes a pair of these. So function takes a pair of these. And what will it produce? It will produce the result type of g, which is b. So it will produce b. So that we have inferred that this is the type of f. Unlike the earlier example where we could resolve that f takes an integer and is a function from integer to integer, fully resolved, here we have it in terms of two type variables a and b, which have to be consistent here. Right? So this is the basic type inferencing. Now let us look into a more formal process of doing this. We are back to the earlier example. So what we do, we parse this program and construct a parse tree, and we use certain specific node notation to make it look easy. For example, we use a special node called fun, meaning function, which is a function abstraction. So the first child from fun is the name of the function. The second child is the parameter of the function. And the third child is the body of the function. So this is the representation. The name and the parameter are customarily shown in red. Now, what you have in the body is certainly what you have here is certainly applications of different functions. So if we look at the bottom, and here, mind you, we want to make things simple to the extent that every function must be of only one parameter, something we have been talking of from the very beginning. And we know how to do that. There are two ways. One is to curry the function. The other is to make n tuple of the parameters, right? So here we are using the curry. So first we need to represent 2 plus x. So we represent 2 plus. 2 plus as a curried version of addition. So we say that I have a function plus, I have a parameter 2, and I'm applying plus onto 2. And this at symbol is a function application. So I apply plus onto 2. What do I get? This subtree. This subtree is a curried version of 2 plus x. So if I give it any x, it will add it with 2. Right? So this is a curried version. Then I again say that my 2 plus x is this curried function of 2 plus applied onto x. And this is the application operator. So this whole subtree of 5 nodes is my 2 plus x. And that is the body of the function add. So this add being a child of fun basically tells me that. The additional information that I encode here is the fact that x is a parameter of add. So x is bound in this. Right? So this is a representation. So far we have not deduced any type or anything. I've just discussed how to represent this function in terms of the parse tree, because I'm now taking it to engineering. So we are talking about what the compiler can do, not only what human or mathematicians can do. So compilers can parse and represent. So this is what one representation that I've presented. In the next slide, we assign type variables to node. Every node is an entity in the program, so it must have a type. So add has a type T0, X has a type T1, T2, T3, T4, T5. T5 is not there because this X is bound to this X. So this has T5 is actually T1. So this is T1 and T6. We do not know what these T's are yet, but this is what we write. Next. Now let us try to put whatever we know. We know that plus has a type int to int to int. So T2 is int to int to int. We know 2 is an integer constant. So T3 is int. Then what do we know? This node function application, if it has a type T4, then we know that T2 applied to T3, T2 applied to T3 produces T4. That is the application. So T2 must be a mapping from T3 to T4. Similarly, here we know X has a type T1. So what is T6? T4 applied to T1 produces T6. So T4 must be T1 to T6. So this is what I know. And what is finally the function abstracted? Function this type T0 is T1 is a parameter type and T6 is a resultant body type. So T0 must be T1 to T6. And you write this down. Right? So you have what you have is a set type variables and a set of type equations, set of constraints. Rest of it is simply solving them. Let's we'll come to the generality, but all that we need is to solve that. So we have these two unknown. So T3 I know it's int, and what T2 I know it is this. So what will be T4? T4 has to be this part, int to int. So I get T4 is int to int. I put that here. Then I have this T1 to, so T4 is int to int, T1 is, or T4 also is T1 to T6. So obviously T1 has to be int and T6 has to be int. There is no other choice. So I put it, T1 is int, T6 is int, T0 is T1 to T6, so it is int to int. So through this process, of course, I've shown the solution in a little ad hoc manner. This can be formalized through an equation solver. But the important thing is through this, I have been able to deduce the type of T0. So after having done this, this is my type declarations that I have got. I'm sorry. And where on my tree, I know these are the types, and these are, I've been able to fully solve this set and get the type of the function add. Right. So that's a formal process. I will in on Wednesday I will more formally introduce how to deduce type for function application and function abstraction and how to keep on using them. But this was just a systematic way in which the compilers can and often do infer types of different expressions. Let me stop here and see if there are any questions. Is there any question, friends, on the type inferencing, the example that we have worked out? No, there seems to be no questions. Okay, very good then. Have a nice day. We will continue on this on Wednesday, and we will show examples of more complex type inferencing and the general principles of the type inferencing algorithm, and what is known as the concept of unification of types and how that plays a role in terms of type inferencing. Okay. Thank you all very much for your attention. Have a good day.